So first let me say it is a pleasure and an honor to be here. I've known many of you for a really long time, some of you longer than I would like to admit. Hi Saul. Many of you I sat in your classrooms. I don't want to remind you how many 3-4.5 decades ago. So what I want to do today is tell you the story of neuroeconomics, and I kind of want to do it in two parts. What I want to do first is just unpack for you sort of where economics was, let's say 15 years ago, and why a bunch of neuroscientists and economists thought there might be some interesting fruit from fusing neuroscience and economics, what neuro would yield. I want to walk through the kind of first round of insights, which many of the people in this room contributed to. And then I want to, in the second half of the talk, dig in a little bit and do a little more real science, and I'll talk you through some current research projects. It'll still be an overview, but it'll be much more sciencey, and so don't freak out if that, just raise your hand and say you're going too fast, or I hate that part. Okay, here's where I want to start. This is someone who inspires me, and he is Blaise Pascal. And I think Blaise Pascal is one of the founders of how we understand how people make decisions. Now, if I was in an econ department, I would probably have started with general equilibrium theory, but I think for decision sciences, this is really the place to start. Before Pascal, we didn't think, in the Enlightenment, we didn't think about decision making as a process, and we didn't think about how it worked. But Pascal was driven to try and understand what made sense when you were making a decision, how you might make a decision well. And he developed something that we nowadays call expected value theory. What he basically said is, if you're choosing between two options, for example, a 50% chance of winning 100 florins and a 100% chance of winning 45 florins, how do you choose between those two? And he said, what you do is you take the 100 and you multiply it by the probability of 0.5. Now, to get to this, he had to invent the theory of probability, but I'm going to skip that. And he said, on average, you'd win 50 florins facing that lottery, and on average, you'd win 45 florins facing this lottery, and so this is a better lottery, and it's the one you should pick. This is a very rational way to go about choosing, and I think at the point that he published that, the actuarial industry was born, the insurance world was born actually in the Netherlands from these insights. This is really great. But it has this problem. And the problem is often, there are two classic ways of stating the problem. One, many of you know, is the famous St. Petersburg paradox. But I want to tell it in a kind of more, I think, moving way. And that is the beggar's problem. So a beggar is walking along, and he's in Paris, where Pascal was, and he finds a lottery ticket. And the lottery ticket says you have a 50% chance of winning 20,000 florins. So Pascal tells us that this ticket is worth 10,000 florins. On average, if you had hundreds of them, they would on average be worth 10,000 florins. A rich person walks up to the beggar and says, I'll give you 6,000 florins for that ticket. Now Pascal says, don't take it, right? Because it's worth 10,000. And the poor person says, it's idiotic. There's a 50% chance I'll have 10,000 florins, and a 50% chance I'll have nothing and be hungry tonight. I'd rather eliminate the risk and go for the 6,000 florins. So that was a puzzle, and it puzzled decision scientists for about 100 years. And the person who really solved that puzzle, I think, was Daniel Bernoulli, the mathematician we know mostly from solving the problem of aerodynamic math. But Bernoulli introduced this really interesting idea. He said, money's not just worth dollars. Money has kind of a subjective internal value that might not always match its objective external value. He actually called this the moral value of money. He said, if we imagine that the moral value of money, plotted here against real money, grows not as a linear function, they're not the same thing, but as a logarithmic function, then we can actually explain the beggar's puzzle this way. See, what happens is the beggar, he is choosing between having this level of wealth, 7,000, and this level of wealth, 20,000. So these are the two different values that he's choosing from. I want you to see they're quite close together because the function has flattened out. This is less than half of this, but it's much closer than halfway to it because of this flattening function. And the rich person is actually choosing between having 10,000, losing 7,000 and gaining 13,000. If you actually map that out, it's 2 points quite close here. The critical insight here is that by this nonlinear transformation of value, Bernoulli accounts for the fact that the beggar says, oh sure, I'd rather have the 7,000 for sure than risk my chance of winning 20,000. And there's no tricks here. It's just this single transformation from objective to subjective value, which allows Bernoulli to capture this idea. Okay, so this gave rise to a huge tradition in Western thought, and this is really utilitarianism, and is really, I think, the cartoon character at the heart of utilitarianism for most of us is Jeremy Bentham. And what Bentham started to do was draw different kinds of functions that related subjective to objective value. And then using those functions, he tried to make predictions about what were more just and less just societies, how we should structure the distribution of wealth in societies, how we should structure the distribution of discomfort and unhappiness in societies. That had a tremendous run through Bentham and, of course, his student, John Stuart Mill, but came to a very abrupt halt at the hands of this guy who's less known outside of economics and political science, Vilfredo Pareto. Now, Pareto, operating at the end of the 1800s, beginning of the 1900s, Pareto took a look at everything that Bentham and the utilitarians had done, and he said, wait a minute, how do you know which of those functions is the right function? You guys have no evidence about that. And if you pick the wrong function, the whole story falls apart. In fact, you have no way to know, Pareto argued, that they have the same function in two people. And so Pareto, formally what he did was he attacked the cardinal nature of these functions and argued that the choice data we have only provided ordinal level distinctions on choice theory. That's kind of more technical than I need to get. But Pareto basically sort of undermined that whole exercise and said, all of choice theory is based on these arbitrary functions. It's a train wreck. Don't ever do it. And choice theory pretty much came to a halt by 1900. And people weren't worried about this idea that somewhere inside of you there's a subjective representation of value because it seemed intractable. Now that changed again. This is an incredibly important point. When economics was kind of reborn in the 1920s and 30s with a school that came to dominate economics for about 70 years called the Neoclassical school. And the person, for me at least, people fight about this, maybe it was DeBrew, maybe it was Arrow, for me it was Paul Samuelson. What Paul Samuelson did, who of course won the Nobel Prize years later for this work, was develop a firm mathematical foundation for building a theory of how you relate subjective and objective value. Now, Samuelson's specific suggestion was that we would never talk about something being twice as good or 4 times as good as 8 times as good. We would just say things are either better or worse. And we determine what was better or worse from you by simply asking you, would you rather have this or that? This would allow us to rank order all the options. And that would be kind of a poor man's version of subjective to objective. It'd be subjectively what's best, regardless of objective state, but it wouldn't be these complicated functions that had been at the heart of the original utility exercise. Everybody okay with that idea? Okay. So that changed one more time in the 1930s and 40s. And the people usually that are cited for that great insight are John von Neumann and Oscar Morgenstern, who wrote a really, really, really famous book published in 1944, where they sort of captured the ideas that Bernoulli had been looking for, but in the framework that someone like Samuelson might have been able to appreciate. And what they basically said was that we could use, in essence, probability, how likely are you to win this, as a ruler to determine when something was twice as good or half as good. So the idea was, if I offer you a 50% chance of 100 florins, and as an alternative, a 25% chance of what? Well, that what would have to be twice as good as the thing that you had a 50% chance on, or you wouldn't say, I don't care, I'm indifferent between the two. And so that might be 200, it might be 250, it might be 300, but whatever it was, the percentage would serve as a ruler that would allow us to map out those functions. Everybody get this idea? So they began with the assumption that what people essentially did was take in probability when they were told about it correctly. They understood what the chances were. That they distorted the subjective value of a game by some probably compressive function, and that you could use this as a ruler to measure the compressive function. Now let me pause here and stress something terribly important in the history of economics. What these guys actually proved was that someone who did this, who used a linear representation of probability and a stable compressive monotonic function of value, would have to show certain classes of behaviors. Put very simply, such a person could never say, I prefer apples to oranges to pears, but pears to apples. Now, a person who shows that kind of preference structure, we call that intransitive in economics, we can prove isn't moving towards any goal in their behavior. There is no goal that you can identify that an intransitive subject is moving towards. And what von Neumann and Morgenstern proved was that if someone behaved as if they did this little calculation in their head and had a stable utility representation, they were maximizing. Their behavior was exactly what you'd expect from someone who's moving towards a clear goal in a stepwise fashion. Okay? So what was great about the theory that these guys introduced, which came to be known as expected utility theory, was that it was extremely precise, it's insanely compact, it has one free parameter in most instantiations. It's the parameter that controls the curvature of this function. If you're a real econometrician, and part of my life I am that, sometimes it has two parameters, but this is not a complicated model. And it's normative, and by normative I mean someone who obeys it is making sense. They're going towards a goal. They're trying to maximize something. Everybody with this idea? And so this was a huge accomplishment. And I think it was the moment of transformation for modern economics for me, at least with regard to choice theory, because suddenly we had an idea of what people were doing when they were making decisions. And we could even begin, if we were psychologists, now psychologists weren't thinking about it this way, to start to hunt for the things inside the subject's brain, like the internal representation of probability and the internal representation of utility, although in fairness, the economists of this generation shunned that idea. They were extremely nervous about that, and they argued broadly against doing it, but more sort of on political grounds, I think, than anything else. Okay, so everything's good, and economics looks great, and neoclassical economics looks great. Then what happens right after this, in the early 1950s, is somebody finds a really, really critical problem with expected utility. And the person who does that is Maurice Allais. Now, Allais was an important economist, is a fantastically important economist. And Allais developed a set of questions that involve lottery tickets, like you have this chance of winning this, and this chance of winning this, and this chance of winning that. And he could ask you, which do you prefer, this lottery ticket or this lottery ticket? And then he could ask you, which do you prefer, this lottery ticket or this lottery ticket? And then he could ask you, which do you prefer, this lottery or this lottery ticket? And he could show that you'd actually made the intransitive cyclic error of picking apples, oranges, pears, apples. So famously, Allais did this at an important economics meeting. And what he actually did was he snuck around at lunch and he asked people these three questions. Really famous economists like von Neumann and Morgenstern. And famously he asked Leonard Jimmy Savage. And Savage, who is the father of our modern theory of probability, took the bait, gave an answer which was completely intransitive, unbeknownst to him. And he's probably like one of the great mathematical minds of the 20th century. And then Allais gets up in his thick Gallic accent, and he gives his paper about the fact that empirically, experimentally, it appears that people violate expected utility theory, and not your common man, who these guys might have cared less about, but all the economists in the room. And somebody said, well, not Jimmy Savage. And he said, no, even Jimmy Savage. Savage famously said, I paraphrase quite a bit, but it's better to paraphrase. Savage famously said, thanks for the heads up, Maurice. I will never make that mistake again now that you have told it to me. And so your comment is of historical interest only. Now this was a huge deal. Because what Allais had demonstrated was that expected utility theory, though concise, normative, incredibly useful, and capable of accounting for much human behavior, didn't work everywhere. And what followed over the next 20 to 30 years was demonstration after demonstration after demonstration of situations in which expected utility theories failed. Just wasn't predictive enough. And so here, an opening came for the next big revolution. And the next revolution, which most of you are familiar with, not least of which because of the recent book about this, was led by Amos Tversky and Danny Kahneman. And Amos and Danny were struck by the failures of expected utility theory and were trying to develop an alternative to it. The alternative they developed, tremendously important in the history of psychology and economics, is called prospect theory. And in prospect theory, they made a couple of strong hypotheses. The first hypothesis they made was that this is supposed to be about probability, that people's subjective representation of probability was not the same as objective probability. That instead there was some really complicated, twisty little function that related these two. This is usually called the probability weighting function. And it usually, in Danny and Amos's original formulation, has two free parameters. They also said, well, I accept that there's some curvy function that relates subjective to objective value, and then you multiply by subjective probability, but they had compelling evidence that there was a reference point, that people kind of thought about the status quo or something like the status quo as a starting point, and they behaved differently when they were gaining things versus losing things. So they broke this function into two pieces, one that curves up and one that curves down. Then they developed evidence that the curvature of the downgoing function was multiplied, let's just say it was different than the curvature of the upgoing function. And so they wound up with about, depending on how you parameterize it, they wound up with about a 5 to 7 parameter theory that you could then fit and predict behavior. Everybody with this idea? Okay, so this is really great in one way. And the way it's great is they were suddenly able to account for all the things that we had been unable to account for using expected utility theory. So that's great. But they've done it by adding about 6 free parameters to the model. So it's kind of less surprising that it works with enough free parameters. Von Neumann famously said, give me 4 free parameters and I'll draw you a picture of an elephant. Give me 5 and I'll waggle his trunk. So Danny and Amos had at least 5. So that kind of makes sense that it worked. But really what was disappointing was not just that it was bulky, but that it wasn't normative. Now, this is a problem because when I say this in public, people are like, what does that even mean? And I've avoided saying non-rational because that's an even worse word, although it's the common word in my field. What's wrong with prospect theory is a person who uses this mechanism to make his or her choices can be proven to be incapable of achieving any stated goal. They are intransitive. The theory requires that all choosers, at their root, be able to say, I prefer apples to oranges and oranges to pears, but pears to apples. No chooser who follows this rule isn't doing that. And for many economists, this was an extremely disturbing fact. Because it says, I think the only way to say it is it says people are idiots. That's the bottom line. And so now you have this tension between the behavioral, what has come to be called behavioral economics, and traditional neoclassical economics. And the tension is that these guys have a really sharp, easy to understand theory that says people are super smart, but it doesn't describe what people do all that well. These guys have a really bulky theory that says people are dumb, but that seems to describe what people do pretty well. And for me, as a neurobiologist, this was a kind of really interesting entry point. I mean, there seemed to be some fundamental disconnect in the field. And I was brought up here by a lot of these people in this room, amongst them by Robert. And I'm going to not use your last name, Robert, so as to preserve the non-use of your last name. No, what Robert Seyfarth was chair when I was here at the end of my postdoc, but was here before that. And one of the things Robert taught me was that animals are under a lot of pressure to be smart. That what they are always trying to do is compete with other animals who are trying to be smarter than them. That an animal who's better at finding berries or fruit beats out an animal who's worse at finding berries or fruit. So for a biologist, the idea that people are at their very core incapable of coherent behavior seems a really weird idea. Now, originally when prospect theory was developed, it was thought that it applied only to humans. But over the course of the first 20 years of prospect theory, there was more and more evidence that animals seemed to show these same weird anomalies. Now this leads in one of two directions. Direction one, animals are also stupid. This, I think, is a relief. Or option number two, the fact that honeybees and humans, separated by hundreds and hundreds of millions of years of evolution, both show the same behavior, even though they have totally different neural architectures, may imply that they show it for a reason. And that it is not totally incoherent, maladaptive, and bad. This is like the title of many a conference on prospect theory, one recently that Joe attended. Why is all human behavior so maladaptive? And the answer is, well, I don't know. That seems like a peculiar idea to hold. But now that we know honeybees do it, I guess we can at least agree that every living organism on Earth is maladaptive. Okay, so I'm obviously setting up a tension here that really bugs me. But this is a core tension in the field today. And if you walk into an economics department like yours here, you can ask, what kind of department is this? My department at NYU is on this side. Harvard's department is clearly on this side. Harvard has a couple of people on both sides, so they're very liberal. But they're kind of known as a hotbed of these guys. Okay, so this is just kind of a fact of life. And what I really wanted to do was try and understand how you could reconcile those two views. What I really wanted was to make sense of all the behaviors that Denny and Amos had found, so that they kind of were logical, like they were towards some goal. But I had no idea how to do that, but I had this suspicion that I might be able to figure something out if I started to look at the hardware, the neurobiological implementation, figure out how we actually make choices, and if we understood how you make choices, maybe it would reveal something about why this makes sense. Okay, now, here I want to pause for a moment and say, not all neuroeconomists hold the view I just shared with you. Everyone would agree up to the division, but just as in economics, there are these two wings constantly trying to kill each other, the behavioral economists and the neoclassical economists. That is absolutely true amongst the neuroeconomists. And so what happened very early on, as neuroeconomics was being born, 25 years ago, was that my gang started to look like the neoclassicists. We were trying to figure out why, and does it make sense, and how do you fix it? And a group of economists who had grown up in the behavioral world, or had really developed the behavioral world, led mostly by Con Kammerer, took the other stance, which was people are dumb, behavior is maladaptive, we will eventually understand why, but neuroscience will help prove that fact. So I think we all kind of went in with the same idea that neuroscience would be important, but the field immediately split, as all academic fields do. Like, if an academic field hasn't split, it's because it hasn't started yet. So the field split according to its traditional borders, and Colin and I immediately set about trying to kill each other. Now, that's not fair. This is a picture of me and Colin together, and I only wanted to show it because Colin is actually a dear and old friend of mine, although we have tried to kill each other many times. Okay. So now what I'm going to do is I'm going to do a terrible disservice to Colin, and I'm going to abandon all of the behavioral neuroeconomists as hopeless losers, and, which I do not believe is true. And instead, I'm going to now follow down our thread, which is can we kind of combine all these interesting behavioral insights that Danny and Amos and their group in the behavioral economics community have systematized, but come to understand them as making sense through some insight from the biology. Now, you might immediately ask, and I hope some of you are asking, why would you think the biology would tell you anything about how people make choices? But what does that even mean? To a neoclassical economist, the biology is irrelevant. I mean, we study choice in economics. We don't study the brain. And it's not clear what the mapping would be from the brain to how we actually make choices. Bob Lucas, a Nobel laureate economist, and one of my heroes once said to me, Paul, you go too fast. I just think we don't know enough about how the brain works to relate brain function to choice. It's just implausible. And I said, well, Bob, I didn't know you read neuroscience. And he said, I don't have to. which I think was a very Nobelist answer. Okay, but I don't buy that. So I'm going to now start with just a strong claim, which you do not have to believe, and by the end of the day, it won't matter if you believe it, but I believe it, and so I got to share it with you. See, this is kind of how I think about knowledge. This bottom layer I think of as you can't really see it on this projector, it says physics here. And I want you to think that each of these layers is kind of a field of knowledge. This is going to be, for many philosophers in the room, sort of straight up traditional theory of knowledge. And the idea is, this is kind of the lowest level description of the world. And lying above physics is chemistry, which is a higher level description of the world, more compact. And above that, biology. And above that, I've somewhat arbitrarily put psychology. And above that, economics, with this black line, the border between the social and kind of natural physical sciences. Now, we do know something about how these levels map to each other, not so much up here between biology and psychology and economics, but we know about it for a bunch of areas. We've studied a lot how physics is related to chemistry, and how chemistry is related to biochemistry. And here's an interesting fact. 120 years ago, if you walked into a physics department and said physics is related to chemistry, they would have said absolutely not. No way. If you walked into a chemistry department and said, I think you guys could learn something about chemistry from trying to reconcile it with physics. I mean, there are very famous papers where chemists in the early 1900s said, that will never, ever work. These are layers of abstractions that are separated. Now, of course, you all know that's not true. Famously, quantum theory allowed us to reconcile the bulk of chemistry and physics, and ideas in chemistry changed and grew from physics. Now, let me add, because this comes up all the time, chemistry didn't go away because physics and chemistry were related. This is a really important point. You might say, gosh, Paul, if you're trying to fuse neuroscience, psychology, and economics, maybe you're really a neuro-imperialist, not a neuroeconomist. And what you hope to do is wipe out psychology and wipe out economics and replace them with neuroscience. That is not my goal here one bit. I'm going to argue against doing that. But historically, I'm going to remind you that the fact that chemistry and physics started to interact, and that these two levels of theoretical ideas began to align, in no way killed chemistry. Chemistry is strong and healthy and alive, and it's better for its interaction with physics. And the same is true for biochemistry. Its interaction with chemistry has made biology stronger, not weaker. And so I'm going to now say, historically the evidence says, if you try and relate lower levels to upper levels, you gain insight, you impose constraints on the upper levels, and the upper levels sharpen. And that has worked for the first three fields that have tried to do it, maybe even the fourth if you include neuroscience and psychology. And I'm going to try and push that story up all the way to economics. So that's going to be my story. Now, our very first effort to do that was actually a paper that Michael Platt and I did decades ago, almost 2 decades ago, where we asked, well, okay, for an economist making a choice between 3 options, what von Neumann and Morgenstern might have argued was that we assign a value, subjective value, to each of these goods. Let's say 3 for an apple, 2 for an orange, and 1 for a pear. And then if someone presents us with a lottery ticket that says, oh, here's a 50% chance of winning an apple, which you like the most, an 80% chance of winning an orange, which you like the second most, and a absolute certain win of a pear, which you like the third most, the way you would make that choice is you'd multiply these 2 numbers together, yield a decision variable, and you'd pick the one that was highest from this list. That's the best option in your current choice set. And that's the thing you go for, the orange. Everybody get that idea? So that's how an economist would do it. Now, a neurobiologist would have taken a very different approach to this problem. He or she would have tried to map the neural pathway by which the apple, the orange, and pears were perceived, where they were represented in some abstract way in the cortex, and how that abstract representation was connected to some output system that produced the actual choice behavior, whether reaching or looking or walking towards the food of interest. And so Michael and I said, well, if those 2 theories are really the same theory, then the place in the middle of the brain where these numbers and these numbers are represented, we ought to be able to go to the middle of the brain measure the activity of nerve cells, and they ought to have these decision variables as their numerical output. So that's a really simple idea. It says something like subjective value times probability is not just as if it's guiding choice, but is really guiding choice, and you ought to be able to go into the brain and find it. And so Michael and I famously did that in the late 1990s. So here's one of Michael's monkeys. I have to say that even then, Michael did not have hair. The monkey is staring straight ahead at this little dot, and what Michael did was he trained his monkeys basically to play roulette. And so what would happen is there's a roulette. Think of the roulette wheel as one that only lands red or green. And so at the beginning, the roulette wheel is kind of spinning. The monkey doesn't know whether this is a red outcome trial or a green outcome trial. We're recording from a neuron that's encoding something about the red outcome, something about the red target. And then the fixation light changes color. This is the roulette wheel, clunk, 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 landing on red. And then the monkey looks at red and gets it. Or it ends green and the monkey looks at green and gets it. So there's a 50-50 chance it'll be red or green. And what Michael varied was the amount of reward that the monkey received when the roulette wheel landed red versus when it landed green. So simple. So here in this group of 100 trials, it might yield 0.3 milliliters of fruit juice in either case. Here, 0.4 versus 0.2, and here, 0.2 versus 0.4. So the idea is really simple. If somewhere in the brain the decision variable is represented, changing the magnitude of the reward ought to produce changes in the representation of that red target, and it ought to be a roughly linear function of those magnitudes. Now, that obviously worked. I don't even have to really walk you through this, but I'll just tell you that this is the average firing rate of one of Michael's neurons when the monkey expects to receive a large reward versus when he expects to receive a small reward. You can see how different the firing rate of the neuron is. The neurons gave us a very clear readout of what size reward the monkey expected to receive at this point in the middle of the nervous system. And Michael repeated that experiment, varying not the amount of juice, but the probability that you'd win the juice. And again, the neurons tracked the probability quite precisely. And in some cases, we were actually able to run both experiments on a neuron, and we could show that a single neuron tracked probability and magnitude and their product. Of course, here, I didn't put this in over Michael's head. I should have probably. So this is me thinking of expected utility theory and thinking, oh, I've actually found the representation of this thing because I found a place in the brain where the economic theory of value correctly predicts what's there. Everybody with this idea? It was a really cool thing, and Michael and I were super proud of ourselves. But, I mean, immediately, there was this strong pushback from the behavioral economists, which is, that's cool. You may have found a place where expected utility theory applies. But what about all the places where it doesn't apply? This is an excellent criticism, because we've got to deal with those. But I'm going to push that aside for the moment, and I will come back to it. Let's see. Now, let me pause for a moment and take a historical segue. So what am I thinking? Or what are we all thinking? There were a group of us by this point. And what we're thinking is, there's some relationship between how much you value something and its true real-world value, and that is probably some compressive function. This is what von Neumann and Morgenstern had basically said. It's what Bernoulli had said. But I was trained here by people like Saul as a classical psychophysicist, in part, and I took a look at that and I said, oh, this is classical psychophysics. The perceptual value is a compressed version of the true value. And that was not surprising to me, because I knew that the intensity of a light that I experience is not a linear function of how many photons it throws off, but rather a compressive function. So the first thing I was thinking when I saw von Neumann, Morgenstern, or Bernoulli was, oh, it's just like psychophysics. Psychophysics is about perception, and I study value, but at the end of the day, they're the same compressive function. Now here, these two guys, Ernst Weber is really the father of, well, Fechner is the father of the mathematics, Weber is the father of the experiments. Weber and Fechner really developed the foundations of modern psychophysical theory. And they were really focused on this. But they also actually drew attention to one other thing I'm going to draw your attention to, and then I'm going to put it aside and come back to it. And that is that if I show you exactly the same light and ask you how bright it is 100 times, you don't always give me exactly the same answer. Right? Your answer varies a little bit. It's as if this wasn't a line, but kind of a varying band. Sometimes a stimulus intensity of 300 yields this value of an output. On average, it yields this value of an output. Sometimes it yields outputs up here. So the response is stochastic and a little unpredictable. It's going to be super important. Now, I should rush to say that while I was discovering this, I was discovering old news. This often happens, of course, to scholars. And as I became a better economist, quite early on, I discovered that Dan McFadden had noticed this when I was still in middle school. And Dan McFadden, who won the Nobel Prize for this work, had noted that the notion of utility and the notion of perception were extremely similar, that they might be the same thing in some ways, and that just as perception seems to be variable, notions of how good something is to you also seem variable, and that these variabilities might be modeled in the same way. And I'm not going to focus on McFadden's insight here, other than, I want to draw attention to him because he's one of my really biggest heroes. Okay, so this is a lot like psychology. And remember variability. Okay, what happened next in the history of neuroeconomics then was a very serious hunt for this vertical axis, places in the brain where subjective value is represented. Now, let me say for any, are there any economists here? You can raise your hand. I'm an economist. Okay, well, you have a very conservative economics department. No, that's true. Okay, so then I don't have to worry about speaking a little loosely. This axis really should be utility, but in the brain we never call it utility, and that's because utility is defined as either an ordinal object or a cardinal object without a uniquely specified zero. These are really important mathematical distinctions. All the theorems rest on these distinctions, and the thing we measured in the brain has very different mathematical properties, and so we never call it utility. We have to find a synonym for utility. We use the word subjective value. Michael and I published a bunch of different names for it, one paper after another, but subjective value seems to have caught. And subjective value, I want you to think of as the same as utility within a linear transform.
Is that different from the concept of salience?
Completely.
Okay.
So let me be clear about that. You have $1,000 in your pocket, and I am going to either offer to give you $1,000 or take $2,000 away from you. Those actually have about the same magnitude of experienced change for most people. Both are equally salient threats, but one is positive and one is negative. This would go negative for the negative thing and positive for the positive thing. So they're different. I mean, there's a really nice story here about how you think about the economics of attentional allocation. And salience then is about information. And there's beautiful economic pieces about this, and I could just now stop and talk to you about Krebs-Porteous information value, but I'm not. Okay. So what happened was, in the history of my field, is that people started to hunt for subjective value in the brain. And Michael and I at that time were doing really recordings in monkeys, so we were hunting in monkeys. But that was about the same time that brain scanners came into wide use. And so a bunch of people began to look for subjective value in the brain using brain scanners. 3 people pretty much found it all at the same time. They were Brian Knudsen, Maurizio Delgado, and Rebecca Elliott. They were all young. Brian had just gotten into a faculty position. The other 2 were postdocs at the time. And essentially what they all found was the same thing. And I'm stealing an image from one of Joe's papers because it's a better image. And they found that there were 2 places in the brain, the ventromedial prefrontal cortex and the striatum, where subjective values seem to be robustly represented in all humans. Now let me be clear, activity in this brain area says how much you like stuff. Whether it's being with someone else, whether it's what you're going to have for dinner, whether it's how much you like money. There are about 400 papers now that explore the representation of subjective value in every domain you can imagine. And every single one of them tells the same story. It's these two brain areas, sometimes others as well. There may be an area up here under some conditions, there may be an area up here under some conditions, but these two areas really seem to be a constant. They're the place where subjective value is represented. Now at this point, I think I felt like we'd accomplished a tremendous amount because we found something that looked like the physical instantiation of utility theory and the location at which subjective value was represented. People started to do probability experiments. Probability was represented there. Michael and my monkey experiments were replicated in humans. It all looked great. But I would go to meetings, and people would say, I grant you that there is some representation of value here, but it's objective value, not subjective value. It's the actual number of dollars. It's the actual number of milliliters of fruit juice. It's the actual probability. It's not subjective at all. It's the true representation of the external world. I would say, why would you think that? Because every psychophysicist knows that the stuff in the outside world gets transduced before it gets inside your head. And so why would you think this would be anything other than your experience? But people were really angry about this. People would take Michael and I and drag us out of the room by our collars, and they would yell at us that this made no sense, that what had to be represented in the brain was objective reality, and that the claim that it was subjective reality was a very extreme claim and one that should probably be dismissed, but at the very least, for heaven's sake, let's begin by assuming objective reality is what's represented in the brain. Now, I probably made a mistake. Michael Doris and I then did a monkey experiment where we used a very, very subtle game theoretic manipulation to prove, using a singularity in the mathematics of game theory, that what it was subjective value. That paper was a disaster. It was a really cool paper, but I learned a lot from no one understanding it. And we returned immediately thereafter to this question of how would you prove that what's represented in the brain is not objective but subjective? And the answer to that question came into my office in the form of Joe Cable. And Joe's idea was, you got to find some place where objective and subjective are really, really, really different. Where everyone would agree that you could tell them apart. And the place Joe was interested in was something called temporal discounting. Now, if I offer you $1 now versus $2 in a week, you're academic, so you might be willing to wait the week for the extra $1, but normal people would say, forget it, give me the $1 now. And we could play this game where we asked, how much, in essence, does the value of $1 drop as it moves away from us in time? And that's different for each one of us, but it's a very steep function. $1 offered at a delay of a week is worth a lot less than $1 offered at a delay of a minute. And so what Joe did was set about mapping for a large group of subjects. Here's a picture of Joe. Using a series of questions that they would perform inside the brain scanner. They set about mapping. I was there. We set about mapping the relationship between subjective and objective value at a single subject level, and then at a single subject level, search for the signature of that individual's subjective value. And Joe was able to prove in a paper that's now, I think, really famous, I don't think it is really famous, that there were two critical brain areas where subjective value is represented: the ventral medial prefrontal cortex, the ventral striatum, and this other area, which is one of Michael's favorite, the posterior parietal cortex, which I'm kind of ignoring for now. Okay? And then this went on and on and on, and people did experiments of this type, and it became extremely clear at the end of the day that these brain areas represent not objective reality but subjective reality, just as Bernoulli had proposed, just as von Neumann and Morgenstern had expected, and just as every psychophysicist would have guessed. And this seemed a real start in the right direction, because now we had a handle in the brain on where the utility-like object was represented. This is a summary of a huge, beautiful meta-study. This is a small, crappy meta-study. That's terrible that Dino Levy and I did first. And then this is a huge, beautiful meta-study that Joe did after he left my lab. And like I called him up, I said, guess what? We have 30 papers. And he's like, yeah, I have 280. And it's already been accepted for publication. This is the best thing that can happen to you. No, I'm serious. If you're a young academic, when one of your progeny does the paper better than you, you should go home and open a bottle of champagne and take the day off.
Just one day.
Well, you don't want to get too far ahead.
What were the areas of the brain?
Yeah, they are the ventromedial prefrontal cortex and the striatum, with a particular emphasis on its ventral subsegment, the ventrostriatum. Okay. So these are other people who come through my lab that did experiments like the ones I described to you that were an effort to map probability. Ifat Levy, who's now a professor at Yale, Ifat did all the original, I think, serious probability studies and showed where probability is represented in the brain and that it's roughly linear in its representation. And Mike Doris, I mentioned, who I think actually did the first subjective value experiment in monkeys and is really what the king of game theory in monkeys, if there could be such a thing. Hannah Baer did some of the critical learning work where we figured out how these values are learned and how they're projected. Brian Lau looked at where other areas of the brain participate and combine information. There's a lot going on. Dino Levy I mentioned already. And I'm going to come back to this guy, Kenway Louie, because Kenway is my longtime collaborator, and I'll talk about that in a moment. The story I want to tell you is really simple. We started to find all the objects of economics. And we started to find them throughout the brain, and we started to be able to write rules about how they come together, and that was incredibly cool. But if I go back to my levels story, so here's the level of economics, the level of psychology, and the level of neuroscience, what we were really doing was projecting down in this diagram. We're using ideas from economics to make a better neuroscience. I think that might have been neuroeconomics or something. And what I haven't told you about is any example of using insights from the neuroscience to change economics. Everybody with that? And I mean, I have to admit that in my heart of hearts, what I really am is an economist, and that's really what I want to do. Now, for the first 15 years, that was clearly impossible, maybe even for the first 20, because we didn't know enough about how to get down into the neuroscience. And all the work was about how you take economics into neuroscience. But now what I want to do is take 20 minutes and go in the other direction and show you work just from my lab that has spent the last 5 years trying to take everything I've told you and bring it up to change the economic theory. And what I'm going to argue at the end is I'm going to show you a different version of expected utility theory that is as simple and precise as expected utility theory, that is normative, and that is based on the neuroscience. It's going to have all the advantages of being able to predict all of Danny and Amos's weird behaviors, but none of the drawbacks of their theory. Okay. Oh, so this is when will we go up? Sorry, that's what I should have said. And the answer is now. Okay, so first I got to start with an image, and I'm going to give you an insight from psychophysics. Before we do anything, I'm going to tell you a little just so story about the perception of images. And this just so story about the perception of images is about a domain that some of you are familiar with called a divisive normalization. Now, this is a picture of another one of my heroes, Horace Barlow. I picked this one because if you look carefully, it says the Royal Society, which is supposed to keep you from stealing it. Those British people don't know that this makes the picture better. And so Horace is sitting there in this picture. And the idea I'm about to tell you really comes from Horace, which is why I picked this picture. Let's zoom in on a point on that image of Horace. I could have picked almost anywhere. And what I want you to notice is that the stuff in this little square all looks about the same. Everybody with that? And if I put that square here, it would look about the same, or here, or here. There are a few places where it would not look about the same, but in general, if I pick any two pixels on this image and compare them, they'd probably be about the same. Let me say that a different way. So here are those 9 pixels on Horace's lapel. Let's imagine we were neuroscientists and we needed to encode in the brain something about that little piece of Horace's lapel. And we're going to do that the easiest way we can imagine. We're going to get 9 neurons, and each neuron is going to have a firing rate which tells us whether it's white or black. They'll fire 10 action potentials per second if it's black, and 1 if it's white. Everybody with that idea?
Mhm.
Okay. Now, let me mention one thing that I just said already, which is that adjacent pixels have a tendency to be similar. Everybody's with that. In fact, if you do this analysis across huge databases of natural images, adjacent pixels are identical about 75% of the time. Just a fact. So let's take a look now at this representation. There are 9 pixels. All of them are black. All of them are therefore firing 10 spikes per second. So you're spending 90 spikes to represent this thing. Everybody good with that? Now let me remind you something else. Action potentials and neurons are extremely expensive. They are the most expensive thing in your body. Your brain weighs just a few % of your total body weight, but consumes 20% of your food. If you wanted to build a brain that was 10 times more powerful, if it was a linear scaling, you would have to triple how much you eat every day, just to support that bigger brain to lug it around. So this is a very important point. You don't want to waste this stuff. You don't want to waste these neurons. You don't want to waste these action potentials. They are the single major cost you face as a living organism. Single most important cost you face. Okay, fine. 9 of these guys, 90 spikes total, 0.75 correlation. Why did you just tell me about the cost of action potentials? This is why I told you that. If this pixel is 75% correlated with this pixel, and you know this guy's firing 10 spikes per second, you know there's a 75% chance this guy's firing. That this is black without even looking at it. Everybody with that? In fact, if I told you that all 8 of these were black, you would know that the center one was black with a probability of better than 99.9%. And here you are spending 10 spikes to tell me something I already know. Now, Horace discovered this in the early 60s. And he said that makes no sense. There ought to be some way, he argued, to arrange these neurons so that they don't tell you stuff you already know. So that what they're telling you is only the unexpected stuff. Now, a bunch of people went at that problem, but the person I'm going to draw attention to, who is largely, usually credited with sort of beginning this thread in the vision literature, is my very, very close friend Dave Heeger. David basically made the following argument in the early 90s. He said, look, this is the outside world. I know it doesn't look like the outside world. For the vision scientists, it's obviously an oriented Gabor filter. It's looking at the outside world, and the outside world is impinging upon this neuron. And this neuron is generating some output. And this neuron is getting another bunch of inputs. These are the inputs from all the stuff around it. These are those 8 adjacent pixels. And you'll notice that these 8 adjacent pixels, there's a division operation going here. What's actually happening is the thing I'm looking at is being divided by all of the things around it. Let me say that a different way. I'll unpack arrow here in a second. The thing I'm looking at is being divided by the sum of all the other things. These other things, this term in this equation, is actually what you already know from looking at the other things. And what divisive normalization does is it sucks out of the representation what you already know using division to divide it out. That's all it does. If you, instead of representing the objective world, represent instead the objective world with everything you already knew about the objective world sucked out of it, what you get was only the most valuable new information. And David made this argument in the early 90s. He actually made it with a colleague of his. They were both at MIT at the time by the name of Eero Semencheli. Eero actually then came here to be an assistant professor for about 3 years before I succeeded in stealing him to NYU. And what Eero basically did was bulk up on this math. And I don't want to focus too much here on the math. I do want to draw your attention to just a couple of things. This is the, now I'm going to restate this the way I think about it as an economist. This is going to be the value of something I'm looking at. This is going to be the values of each of the other things that I could choose. This is going to be what we would call in math a covariance matrix. It's the degree of relatedness of the different things. And this is going to be a really important term. It wasn't so obvious why it was important in David's day. David's day is my age. When David first wrote out the equation, this little term is just a balancing constant, but you're going to see it actually does a really interesting thing that none of us anticipated at the time. Okay, so this was really cool. Arrow proved that efficient representations use this form. Let me say that one other way, because this is a really important point. What Horace said was, animals ought to be efficient in their use of action potentials. You ought not to waste them. This respects the fact that action potentials are costly. And what I'm telling you is, value is not useful if it is represented wastefully. Value is useful, most useful, when it is represented efficiently. I'm going to leave that idea because I'm going to build on it. Okay, so this notion, which came to be known as divisive normalization or efficient coding, turned out to be a ubiquitous feature of the nervous system. After Arrow and David wrote these papers, people began searching to see whether or not the representation of sound intensity obeyed this efficient representation. And they found that in cortical area A1 and A2, that was the case. And people began to look systematically at cortical area V1, where visual images are represented, and V2, and V3, and V4. These are clever names. V5 also exists and is efficiently represented. Every place anybody looked at a sensory representation, this was the rule. And so we immediately began to wonder, gosh, would this be true where the values of choices, like the ones Michael and Joe had studied, are they efficiently represented? The idea here was that what was being represented when we offered a chooser the opportunity to choose between option 1, option 2, and option 3 was not their true value or even their compressed value, but their value divided by the sum of all these three values plus a constant. Details not so important. And so what Kenway and I, so this is work that we set out on about 5 years ago, and it's been done with my long-time collaborator Kenway Louie, who's at NYU. And so Kenway and I immediately began to search for evidence of this kind of a representation in the areas where we had previously seen economic representations. Now, we have published a ton of papers on this. I'm going to tell you one story. In this example, a monkey is looking at three options, and these three options have different values. This option, let's say, is worth 1. This option is worth half. And this option is worth 2. Okay? And sometimes I'll show you one option. Sometimes I'll show my monkey 2 options, and sometimes I'll show my monkey 3 options. And I'm always going to be looking at what this neuron is telling me about this option. Okay, so here are the situations I can generate. I present this option alone. I present it with one sort of distractor that's of low value, one distractor of high value, or a low value and a high value together. I can even create a situation where where there's nothing here, this is worth 0, but normalized by a low value, a high value, or both. And here's what neurons do when they're faced with the task of representing the value of this option up here on the number label 2. This is the firing rate of a single neuron when a single target of value 1 appears at that location. If I add a low value target as a distractor, you can see the firing rate goes down a little bit. That's because the thing not in the numerator but the denominator has grown. If I put a big option there, it goes down some more. If I put both, it goes down some more. And if I instead go to a situation where there's nothing there, adding these distractors in again pulls it down. Come on, little back. Now, I will not belabor this. For the neuroscientists in the room, let me say that we've done tons of papers on this, but one of the ways we've assessed whether this is a good way to describe the neurons is we've compared observed activity versus predicted activity using different models. So we'll take a model and we'll try and predict the activity of the neuron. And we'll ask, what's the best model? The old one Michael and I had originally proposed. This is the one probably most famous for the work of Mike Shadlin. Poor Josh was forced to work on this model for many years. And this is kind of the full-bore normalization model. And what I want you to see is that the normalization model outperforms any model in the literature, and it does so by just a huge amount. This is the way the neurons in the parietal cortex at choice areas are representing. They're not representing true value, they're representing true value divided by the sum of all these other values. These are all efforts to kind of develop this idea more. I'm going to skip ahead and show you a couple quick experiments, because I know I'm now 58 minutes in, and I'm supposed to be done in 2 minutes, right? The next step for us was asking, well, if that's true, if that's the nature of the representation, does it predict wacky behavior of the kind Kahneman and Tversky had originally imagined? And so this is an experiment Ken Wei and I did, where in essence what we did was we had people tell us how much they liked different kinds of snacks. So we could figure out what their favorite snack was, and their second favorite snack, and their third favorite snack. And then we asked them to choose amongst groups of snacks. And we had very detailed mathematical predictions of errors they might make if our model was correct. And it turned out that our model predicted all kinds of weird idiosyncratic choice behavior of the kind Kahneman and Tversky had first laid their hands on. It predicted them with much greater precision. And it did it based on the assumption that what these neurons were doing was representing not the true value, but the normalized value. Now, I'm going to skip ahead again and say that we have also looked at this for what happens when choice sets grow large, and we've predicted the curse of choice with tremendous precision. We can actually fit the curse of choice data sets. This is a paper under review right now in an economics journal. We can predict the curse of choice better than any known economic model, as well as better than the Kahneman and Tversky class models. I'm not going to tell you about this, but we've also then begun to ask, how would the brain compute this stuff? And so we've built networks of pseudo-neurons and asked, how would you wire them up in order to compute these things? It turns out that the wiring diagram is extremely simple. This is a classic wiring diagram 1 million people have used. And we were able to prove mathematically that the kinds of diagrams that people have been drawing for about 20 or 30 years actually generate networks which have one unique solution, and that single unique solution turns out to be the normalization equation. Even better, this normalization equations in their dynamic form even predict the moment-to-moment fluctuations in neurons when they're looking during a decision at different kinds of options. Okay, so now I'm going to bring the train home to the station. So if everything I told you is right, I ought to be able to write out this equation and use it to understand what Kahneman and Tversky were doing when they built that 7-parameter model. And this is work that I've done with another longtime collaborator, Agnieszka Tamula. And here what I'm doing, it's a little hard on this projector, is plotting the normalization equation. And what I want you to see is this curvature looks a tremendous amount like the classic Kahneman and Tversky function. But this curvature looks a lot like the classical Daniel Bernoulli function. Sometimes people argue that choosers look like expected utility choosers. Sometimes they say they look like prospect theory choosers. You know what turns out to control in the normalization equation, the shift from this to this is how many neurons you have. When you have more neurons, the thing gets steeper, and when you have fewer neurons, the thing gets shallower. So the shift from expected utility theory to the prospect theory style value function seems to depend exclusively on what we call capacity. Now here's a neat thing. This model shown here has only one free parameter, and that's the capacity term. Unlike Danny and Amos' version of this, which had, for this particular thing, about 3 free parameters, 3 or 4. Now our model does have one other free parameter, and that's the expectation, how much you expect to get. For those of you who know about choice theory, you know that expectation is tremendously important, and it is in our model too. It turns out that this is computed by the network in a way we understand. It has to do with recursion in the network, comes out of the differential equations. This is a shift in the reference point. this is actually not really a free parameter. This is a change in the reference point, and we totally understand it. You can model it at the level of neurons or at the level of equations. The only thing I want to take home to you is this does everything that Kahneman and Tversky's model does. And when we run it against Kahneman and Tversky's data in the most famous data sets in the literature, it outperforms it. And it does it with one parameter, which is this capacity parameter. Now, for those of you who have some economics training, it's a very weird model because preferences are not stable in this model, and we could talk about that. But for me, this is a really big deal because now I've achieved half of my goal, which is to kind of understand from the neuroscience why the kinds of curvature functions that Danny and Amos were looking for arise. But what I haven't told you yet is why they make sense. And I'm not going to tell you too much about that, but I am going to tell you that a paper under review right now that one of my postdocs, Kai Steverson, and I have written makes the very detailed mathematical argument using a traditional economic axiomatic approach. It proves, in essence, that the class of equations we've been studying are the optimal solution to how do you represent redundant information when the quality of the representation is costly. It turns out there is a single unique answer to that question, and it is the class of functions in which the normalization equations reside. That is really important because for me that's the last piece. Remember, my goals were to explain neurobiologically how the phenomena that prospect theory seeks to explain arose, and then to explain why it makes sense. And it turns out, and it took Kai and I 3 years to figure this out, it turns out that let me put it this way. Von Neumann and Morgenstern, when they wrote expected utility theory, got it wrong. It doesn't predict behavior. What did they get wrong? What they got wrong was they assumed that infinite precision was costless. That being perfect at always saying apples, oranges, pears was easy. As soon as I tell you that every time you want to get a little better at apples, oranges, and pears, you have to pay more to get better, you'll get to a place where you say, I'm not willing to pay any more. I'm getting it right 99% of the time. I'm not willing to pay twice again for 1% more improvement. And the equations that solve that problem turn out to be the normalization equations. Now I've cut some corners here. The normalization equations mutated a little bit over the years. These aren't actually Hieger's equations. They're very close to them. But I think that the story here is exactly what I wanted to start with. The beginning of the story was what neuroeconomics was economics pushing down into neuroscience. But what I've told you about from the last 5 years in my research group is the opposite direction. It's using what we know from all of neuroscience, from sensory representation, from cortex, and what we learned from economics, rebuilding economic theory and recovering what was so great about economic theory. Now we can account for all the anomalies, but they aren't stupid. They're efficient. They're mistakes that make sense because they're the trade-off that incorporates costs. And I've shown you that at a bunch of different levels, at the level of biology, at the level of psychology, and the level of economics. For me, what really happened over the course of the last 20 years was I should do it this way, is we really strove to drive these 3 layers of understanding into perfect alignment. And each time the layers come closer to alignment, we gain new insights that echo up and down through the representational structures. So now we're at a place, I think, I don't want to say that expected subjective value theory is the last theory. It's certainly not. I would rather like to think it's the first theory that reconciles layers, and that future theories will take the same approach of finding the flaws in our theory, but finding it at all kinds of different levels and forcing them together, whether you're operating at the level of biology, psychology, or economics. Thanks very much.